Here are three items that I found on the internet. So pause the video and read through all three of them. And then after you're done reading, come back and I will comment on them. So each one has its strengths and its weaknesses. Let's do the first law. Every body remains at rest or uniform motion unless it is acted on by a net external force. So this one is good because net external force should be in there. Whereas this one they say an unbalanced force. And here they say an external force. This is actually the weakest because you could have an external force. You could have two external forces that cancel each other out. So it should be an unbalanced force, or this is actually saying it in the best way, a net external force. But then when we read this one, it says at rest or uniform motion. Well, what does uniform motion mean? So in that sense, this one is better. It says remains, an object at rest remains at rest, or an object in motion remains in motion in a straight line. But even there's a weakness here. The motion should be a constant speed, right? A constant velocity. And a body at rest will remain at rest. A body in motion will remain at motion unless it is acted on by an external force. So in my opinion, none of them are perfect. It should say an object at rest will remain at rest. Objects in motion will remain in motion in a straight line at a constant speed unless acted upon by a net external force, an unbalanced force or a net external force. Okay, the second law is an equation, F equals ma. Okay, this one isn't so good because the F should be capitalized and they should both be vectors. And it should be the summation of the forces. And this one has the capital F and the A, but they should be bolded, maybe they are, to show that they're vectors, and it should have a summation sign. And this one has the F, the M, and the A, but it doesn't show the vectors and it doesn't show the summation sign. So what we know is that our equation, the way we will always use it, is the summation of the forces vector equals the mass times the acceleration vector. And then we will separate it, I don't have space to do this, but into two vector equations. So the vector will be the sum of the forces in the x direction equal m times the acceleration in the x direction, and the sum of the forces in the y direction, no space, equals m times the acceleration in the y direction. And this is the thing that we're going to be using again and again and again, not only this week, but next week and the following week and all the way till the end of Physics 2. This is a really powerful and important equation. It's the first really basic fundamental law of physics that you've seen. This equation works from the smallest atomic and subatomic particles to the largest systems of galaxies in the universe. It's a universal relationship. And notice it's a relationship between force, mass, and motion. So we're going to talk a lot about that. Force, mass, and motion. This is the relationship between them. And mass, of course, is inertia. And so none of these mention it, but the first law is sometimes called the law of inertia. And so if the boy on the skateboard is in motion and the skateboard hits the rock, the natural tendency of the boy is to move in a straight line at a constant speed. So he's not thrown off the skateboard. No, he just keeps moving in a straight line at a constant speed because there's a force on the skateboard, but no force on the boy. Okay, so force equals mass times acceleration. So this is the symbolism we want to use. And then the third law, so keep in mind, the first and second law, this is an important point, doesn't tell us anything about force. It just tells us that there's a relationship between force, mass, and acceleration. And it also, another important part of this, I'm going to make some space for myself, is that if we take this law and we rewrite it for acceleration, so the acceleration that an object has is proportional to the net force, that means the sum of all forces acting on it, divided by the mass. So if the force goes up, the acceleration goes up. If the mass goes up, the acceleration goes down. So mass, we can think of mass as inertia. And inertia is resistance to change in velocity or acceleration. So the boy has inertia. And so when the skateboard hits the rock, the boy keeps going. And the more inertia the thing has, the more force it takes to stop it. So that comes out of the second law, and that's another very important thing that you'd be doing in the assignment. Mass is the same thing, equal to, or the same thing as inertia. They can be used synonymously. And inertia, if you're asked to define inertia, it's resistance to blank, change, right? That's the way you think of inertia, resistance to change. You're lying on the couch and you don't want to get up, you don't want to change, but resistance to change in what? Resistance to change in velocity or acceleration. Change in velocity is acceleration. And notice, change in velocity can be an increase, a decrease, or a change in direction. Velocity is a vector. So I often use the example of an oil tanker, which is very massive, has a lot of inertia. So the oil tanker is very difficult to speed up, equally difficult to slow down, and equally difficult to change direction. Any of those things requires a force, and if the mass is enormous, the acceleration is going to be tiny unless you have a huge force. So it's very difficult to change the speed or the direction of an oil tanker, or for that matter, a big loaded freight truck. Whereas a motorcycle, right, it can accelerate very fast, it can stop very fast, it can change directions very relatively easily. Okay, so now let's go to the third law. So the first law, the law of inertia, the second law, the equation. The third law actually is the only law that tells us something about force. And most of these they all have action, reaction. Okay, so for every action there's an equal and opposite reaction. For every action there's an equal and opposite reaction. A exerts a force on B, then B exerts an equal and opposite force on A. And it shows you the example of the dog pulling on the man. And if you put a tension meter or force meter on the leash, then the force of the leash pulling back on the dog, same leash, is equal to the force of the leash pulling forward on the man. So in this case, I guess we consider the man the action and the dog the reaction. But I have what I think is a better way of stating this law. Let's get some space. So this is about the nature of forces. And so this is what I'm going to say about forces. try not to. Remember, the first two things is the relationship between force, mass, and acceleration. Now we're going to talk about force. How do you think about force? The entry-level sort of third-grade science class words are push or pull. A force, every force is either a push or a pull. And in order to have a push or a pull, you need two objects. You can't push yourself. Well, you can, your arm can push your shoulder, but you can't push yourself. And if you want to move, what do you need? You need the floor. So if you're suspended from a rope and you try moving your legs, it's not going to do any good. The reason your legs, it's not your legs that move you forward. Your legs push against the floor, and the floor pushes back on you. If you're a swimmer, how do you move forward? Oh, you push yourself forward. No, you don't push yourself forward. You push on the water goes back, and you go forward. Without the water, you couldn't swim. And if you're a bird, you have to have big wings, because when you push on the air doesn't have a lot of mass. So the bird pushes on the air goes down, and the bird goes up. So there'll be lots of examples in the Minds on Physics exercise where you'll do this. So remember, a force is always two objects, and the objects interact. So the action-reaction is actually better thought of as an interaction. A force is an interaction. A force is not something that you can possess. You can't buy it or sell it. You can't keep it in the drawer. You can't keep it in a toolbox. A force comes when one object interacts with another and pushes or pulls on it. And if you pull on a wrench, the wrench pulls back on your hand with an equal and opposite force. If a ball hits a wall, the ball pushes on the wall, and the wall pushes back on the ball with an equal and opposite force. So all forces are interactions between objects, and the objects push or pull on each other with an equal and opposite force. And in the MOPS, there are certain list of forces that come up again and again and again. And so in order to use Newton's second law, this equation here, we need to identify the forces, right? Because we have to add up all the forces. So in order to use Newton's second law, in order to solve problems, we do force diagrams, but we don't call them force diagrams. We're going to call them free body diagrams. That's the standard. So force diagram, I'm not going to write it out, but it's a, well, I will write it out. Free body diagram. And we'll usually just go FBD. And so if you have a book sitting on a table, that's the diagram. But the free body diagram would be the book. And the table pushes up on the book, and gravity pushes down. And so that's a force that we'll see a lot of, Fg. And you calculate it by the mass times g. And when a surface, a table, a floor, a road, a wall, pushes on something, it's called a normal force. So we call it Fn. And keep in mind that normal means perpendicular. It's just a mathematical or physical word for perpendicular. And so a normal force is when two surfaces press together. But sometimes when surfaces press together and you try sliding this thing, there'll be friction. So if I'm sliding this, supposing I push this along the table, but I push it at constant speed. So I'm sliding the box or the book across the table at a constant speed. Why isn't it accelerating? Because there's an equal and opposite force, and you know what that is. That's the force of friction. MOPS calls it F fric. I will call it F sub F. And then the other kind of force that you'll often have is, instead of pushing on the box, I'll attach a rope and I'll pull on it. And so now, if I'm pulling it with a rope at a constant speed and I'm pulling it at an angle, then the free body diagram, I'm going to have to make some space. Just move this stuff out of the way. The free body diagram of that box now would be a tension force. The floor is still pushing up, so a normal force. There's still some friction. And don't forget the force of gravity. And if I'm pulling on this at a constant speed, then because it's at an angle, we have to find the components. There's a component of the tension force this way, and a component of the tension force that way. And so now, what has to be equal? What has to be equal is that the force of friction has to be equal to the x part of the tension force, because there's no acceleration this way, and there's certainly no acceleration this way. So in this case, the normal force, plus there's a little bit of lifting up, right? The tension, the y part of the tension force, these two forces have to add up to equal the force of gravity, because they have to be balanced. Why do they have to be balanced? Because the box is sliding at a constant speed in a straight line. Okay, let's summarize and end. So we looked over statements of the three laws. We discussed each one of them. I kind of adjusted these a little bit. And what I told you, what's central to all our work that we do is this equation. And so the format for problem solving almost always is to draw a diagram. Whoops. Okay. I wanted the pointer to draw a diagram. Then, since we're studying this, draw a free body diagram of the object. So this is step 1. Draw the diagram. You'll see this on your equation sheet. Step 2 is draw the free body diagram. And step 3 is to write this equation. And usually you'll see it in a lot of the documents. I write it this way. The sum of the forces equals ma. And then I separate it into the two equations that we will use separately to solve problems. This is the formatting that you'll see me do when I solve problems. And this relates directly to what we did last week. We always dealt with the x part of the projectile separate from the y part. So just remember that. Why? Because they're different. In the case of the projectile, the force in the x direction, no air resistance, there was none, so the acceleration was none and the velocity remained constant. And there's a force down, so the projectile was subject to a constant force down and a constant acceleration down. And that was the nature of projectile motion. So when we study problems, and a lot of the exercises in the MOPS looks at this equation in two ways. One is, what happens when all the forces are balanced? That's called balance or equilibrium, and it means the acceleration is 0. And so two ways. If you know that the forces are balanced, you know the object isn't accelerating. if you observe an object which isn't accelerating, you can automatically infer that the sum of the forces in all directions, if it's not accelerating in any direction, is 0. And so with projectiles you saw, it didn't accelerate in the x direction, so there was no net force in the x direction, but it did accelerate in the y direction, so there's a net force in the y direction. And so this week we'll look at mostly balanced or equilibrium conditions, but next week we'll look at a lot of cases where there's an unbalanced force, and there's a net force and there's an acceleration. Okay, we're done.